All right, 6 o'clock. Let's get started. So welcome back after the midterm, post-midterm sessions. Uh, and how was the midterm? Anyone wants to comment? So no comment on the midterm. Okay. All right. I didn't hear anyone. Anyway, so let me start with the poll tonight and see if you are, if you have actually went through our topics for tonight. Okay, let me announce the poll for a minute. Let's wait for a couple of more seconds. Then I can share the poll result to you all. Okay. So you see that it's good that lecture videos are being watched by more than 50% of you. Wonderful. And 60% of you has gone through the lecture note. That's great. Okay, we don't have any question. Okay. So as you probably understand that whoever went through this part of this lecture, we have switched the gear. There is nothing like assembly language or anything. We'll be dealing with that anyway in our project, but we have switched the gear in the sense now we are trying to explore more like how this magic happens inside the processor. So what we did in the pre-midterm, that we used assembly language to explore underlying hardware features and models, like try to understand the hardware basically from whatever facility they are providing through the very low level instructions, like you have used add, jump, BNE, those kind of things, like, and try to explore and understand what goes on inside the machine and how they basically interact with each other, different components like the memories and the processor. Those kind of things we try to explore in our pre-midterm era. In the post-midterm, what we'll be doing is how things are done exactly, how things are done exactly. And we start this thing from this CS47. We'll explore and we'll stop at the level where we'll see that how the integer mathematic operation like integer addition, subtraction, division, multiplication, they are done at the hardware level. And then we'll continue this whole journey towards the 147. 147 basically we'll explore more and see how we combine all these things together into a microprocessor that can actually execute your given program. In my 147, if you take from me in future, you will see that previous part, like pre-midterm part, is probably 80% identical with what we'll be doing post-midterm here. Like it will become like more like a review in that class 147. And in that class, we actually will design and implement one processor from ground up, from the scratch. Okay, so basically, what I'm trying to tell you, this is not the end of your journey. It is basically just a start and beginning of your journey, and we'll continue this whole thing in the 147 start. So for that, we started with the exploring the Boolean algebra, because like underlying hardware is an electrical engineering discussion. Okay, and we are not ready for that electrical engineering discussion. We will limit ourselves in the whole of this hardware study throughout the 147 is on mostly onto the logic level. Okay, using the logic level, we'll try to understand the hardware from the logical perspective. That's our goal is from this point onward. And while doing so, while we'll be studying this, how this addition, subtraction, multiplication, divisions are done at the logic level, we will implement the project. Okay, so as a hands-on, and what we'll be doing in a nutshell, please go through the project description there and watch the video and all this stuff related to the project. But in a nutshell, what we'll be trying to do, we'll try to write an ALU procedure, like a procedure ALU, conceptual procedure, which will evaluate these mathematical operations like addition, subtraction, multiplication, division, without using any mathematical operation like add, subtract, those things. We'll only use logical operation to implement those that ALU routine, ALU procedure routine at the mixed assembly level. So that is our target, and hopefully by doing that hands-on, you will have more understanding and clear understanding of how things works, at least at the ALU level, how the ALU crunch out your mathematical operation numbers. Question? All right, now, so this is like Boolean algebra review. This part, today's part is most likely review of your Math 42 or equivalent study, that is logic algebra. Okay, logic algebra. Next part, Boolean algebra 2 is more related to the digital design side with the K-map. Maybe they are new to you, maybe. I'm not sure. Okay, so basically, oh, I have some chat comment. I don't usually see that. Okay, I'll come back to the chat comments. Anyway, so basically, next part is probably going to be the newer one, and most likely the K-map technique and all this stuff will be new. Please make sure you understand that part very well to go forward. Now, today I'd like to discuss mainly two topics. If you don't have any question, let me first check if you have any question on the discussion. Okay. So ours is module 5 now, right? Module 5, no, module 5, I don't see any question there. Okay, that's fine. I'll basically try to do two things to you tonight. Is first of all, let me see, participants. Okay. So I hope you can all see the Jamboard. So one is the concept of your of the Boolean function, right? So often we write Boolean function like this, like if x, y, z with some Boolean operator, right? X bar or yz, and we derive like truth table out of it. Like sometimes probably you have, if you remember in your logic class, the math 42, the logic part of it, logic algebra part of it, I hopefully you came across the concept of the truth table. So we do the similar thing here. Let's say we do the truth table x, y, z, and we're talking about the f as a function output of that. And what we do, we basically list down all the possible logic combination of these Boolean algebraic variables, and try to and also note down the function value, function outcome of this combination. So let me write down all the combination of these three variables. Since there is three variable, Boolean logic combination will be 2 to the power 3, 8 rows there. So there will be 2 to the power 8, 3 equal to 8 rows in the truth table, right? So 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so we got our 8 rows. And then we can actually stick in the logic values in this Boolean expression and evaluate the function value and write them, right? So let's write the function value. 0, 0, 0 is, so I can see that if x is 0, function value is going to be 1. So wherever there is 0, x is 0, I can just, without any further evaluation. And if my x is 1, then my functions are then I need to see yz. If this combination is 1, then my function would be 1. So only this guy, this logic combination will give that. So this will be 1 and the rest of them will be 0. So this is like we are deriving from a given function with an expression. So this is an expression-based function definition, and this one is truth table based function definition. So this is the probably one of the important concepts that we need to catch up. Like people usually tend to think that like it is kind of an one-way conversion. Like given a expression, we do that, we can construct the truth table. Actually, that's not true. Basically, both these and these two representations are the representation of the same Boolean function, but two different forms. One is expression-based function definition, and another is truth table-based function definition. Given that, that means our conversion can be vice versa. Okay. So for example, like if I go with an, just let's put an arbitrary truth table. We start with a truth table based function definition. Okay, and let's again put the combinations there. One zero one 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 zero one one one. Let's say somehow we come up with a truth table like this. Okay, so this is a function. This is a function, just like this, just like this. This truth table is a truth table based function definition for f. Now the question is how this f x y z. Remember this. This is my input columns. These are my input variable. Question is that what is that expression corresponding? Like, how can we come up with a Boolean expression from here so that if we reverse transform it, like that Boolean expression in the truth table, we end up here. And that is the main discussion on the next lecture. Okay, and that is how it is important, and that is why it is important for digital logic era. Because like from, let's say we are trying to develop a logic circuit, okay, logic circuit which evaluate some logic functionality, and that functionality is defined in words. Usually we'll see, like down the lecture 3 4 lecture down the line, we'll see the digital logic circuit design topics. But in a nutshell, there is some like verbal description, like a plain English statement that I want to make a digital machine which does this, which responds like this upon this logical input. Okay. From that description, first thing we make is a truth table. And from there, we try to convert that truth table representation of the function to then minimized Boolean expression based function definition. So we need to do minimized, this is a minimized Boolean function we need to derive out of the truth table. How are we going to do that? That's the topic of the next lecture, and we use a technique called the K-map in the digital design era. But anyway, you'll see that K-map is not the ultimate solution. It's basically the stepping stone towards the different other complex algorithms that modern tools follows. But that's kind of a very basic thing we will be dealing with, the K-map. Okay, just to clear up the concept, how from a description into a digital circuit, this whole design process steps goes through. Question? All right. Next one then. In this lecture, I think one part I want to mention with you is the consensus theorem. Consensus theorem. So consensus theorem this theorem is very handy sometimes if you actually reducing a Boolean expression on paper pencil using the identity rules. It goes like this. XY or X bar Z or Y Z equals XY or x bar z. So practically this term we can just drop immediately if we find out such expression in a while we are reducing a algebraic term. So how do we remember it? Just I go with some very lightweight analogy there. Let's say like this guy X and Y are friends, okay, and X loves to party. Okay, X loves to party. So that means what we can tell about the nature of the Y is probably love to party too, because same nature, people comes together and like friendship bonds and all this stuff, right? We all know that. Now the X bar, on the other hand, that means what we can tell about the nature of the X bar. X bar is not party going, it's probably more library oriented, let's say. And that is a friendship with a Z. So Z means like it's a library going people, right? Now we are trying to mix a party loving people with a library loving people. And most probably that friendship will not stand, right? So that's what, just as I said, is very lightweight analogy anyway, but that's how I remember this consensus theorem, that they're not going together, they cannot be paired up. Okay, so this is consensus theorem, and we can prove it, like if you have studied that, we can prove it very easily with these our basic identities YZ. And now what we'll do, we will basically make this YZ expanded with X bar X. So this part actually gives us one more valuable lesson, that to make minimization using the identity rules, sometimes we need to expand and then contract. It makes life easier. Then you don't always expect that you will basically reduce at each step. There might be possible, like just think of the possibility, there may be some step where you need to expand a little bit to further contract. Okay, so that's one lesson we should pick up from here. Okay, now we write it down like this one would be, we'll expand this guy, right? So it becomes X bar YZ and XYZ. So what we'll do, we will pair up these two and these two. So that means we'll have XY or XYZ or XZ, X bar Z, X bar YZ, which is XY, 1 or Z. This is X bar Z, 1 or Y. So this is XY and 1, X bar Z and 1, which is XY, X bar Z. So see that our this term, little guy, is just vanished, right? So this is your consensus theorem. Question. Okay, now let me look at the chat. Yeah, the text took a while to type out. Paper was okay. I see, like, yeah, that can be challenging as an online exam, typing the question on the canvas board. I was expecting more like possibly you didn't try to write down the midterm answer on the paper as a whole. Like I was expecting that you guys all use the paper as a scratch notes and then actually finally typing out on the screen. Basically, that was my expectation. I'm not sure. So that's why like I wanted to give you the practice midterm and see like how you do there. Uh, Maybe you can type nowadays. I'm not sure about the other classes how the exams are going on, but this subject is little more theoretical as it is. So we cannot do all multiple choice type questions and short questions. So definitely there will be problem solving questions. So one way to do like bounce back in the final from these difficulties would be to just to practice like you have the problem sets, practice the answer typing on a Wattpad or something, so that you can time it and you can sync your process. That's the only advice I can give you. Yeah, it was long, almost couldn't finish it. Yeah, maybe it depends, right? It depends. And also remember again, as I told you, these exams, midterm finals are basically differentiate between the best, better, good people, right? So it will be longer, like who can do faster, who can actually like come up, recall the information faster. That's the one thing, right? It is your understanding part is more covered with the other part like a quizzes, your programming assignments and stuff like that. But this part is more like how much you can recall, how fast you can recall on the informations, and also how clear on your understanding, so that you can do the problem very fast. So those are the two aspects of these exams anyway. Okay, all right. So I don't have anything much tonight. Then we can probably stop here. Possibly next day we'll have more question, and then we'll discuss. Okay, one from T. When will you know the result from the midterm? Oh well, I need to find out to grade them, right? So let's see. Let's see. Okay. Usually, like on average, with the past semesters, it's probably 2 weeks turnaround for me. Um, yeah. So let's see how does it go. Is there a practice final? Maybe I haven't decided. I will probably give you practice final. I will, as long as I have time to set that up, right? Then I have to set up both final and practice final. So yeah, double work for me. But I'll try my best to do it. What do you mean by it is going to be unlocked? Means I haven't created any yet.
Oh, I mean, for the practice midterm, you locked it after we took it.
Oh, that's the practice quiz. So what you can see. So maybe can someone please explain your what is that? Your observation on that, like you took it like a midterm environment, and then as a result viewing process, what did you see there?
Once we were done taking it, it just locked you out, so you got one chance to look at it.
Okay, so that means you need to log in back or what?
Well, it just means you took the practice midterm,
Okay.
and then you got to see the results in Lockdown Browser one time, and then after you close Lockdown Browser, you can't see them again. It's currently how it is.
Oh, okay. So basically you opened up the lockdown browser, took the quiz, you complete, you submit, and then lockdown browser did not close, but basically showed you at least MCQ answers, correct, false, etc. Right?
Yeah, but now we can't see the questions again either. So
Oh, okay. That's the part. Uh, mhm. Yeah, let me see that. Or yeah, we can do that. Or not. I need to find out. Like it's a practice quiz part of the session. I need to figure out what can be done.
Okay, thank you.
Okay, then we'll stop tonight.